Okay, we should get started.
Sure.
Ajin,
Yep.
take it away.
Okay. So today I will talk about the model-based search methods, and if time permits, I will talk about an application to RL.
Louder?
Louder?
Louder, please?
Sure, sure. Yeah. Yeah. So it has nothing to do with the model-based approach you see in RL. It's a optimization algorithm. It's randomized optimization algorithm. So you see gradient descent like algorithms where it's not randomized. So we see if I put some randomization into the optimization, how does it go? And we are just going to see just an optimization algorithm, see how it goes. So first of all, it has nothing to do with the model-based approach you see in RL. So let's see. So the problem statement is just like the standard optimization problem. So you have a function h, and you want to find x star. So maybe it's like take the maximization problem. So there is the only issue here is that the function h is unknown. So we say it's an oracle exists, and it just gives you the function value when you give an x to it. So for technical reasons, I will assume that x is just a compact set, and the solution x star is unique, and it's in the interior of that feasible region. Okay, so we have the first result for this kind of problems. It is NP hard, and you don't need to solve anything further than that. So if it is NP hard, you don't need to do anything. Yeah.
Also mean a multi-model is non.
It has multiple extrema. Okay, so they didn't literally say like that, but what they said is if the function is k differentiable, and if there exists an algorithm A which can give you a solution in epsilon precision, then the number of steps you need is exponential in the inverse of the precision. So m is the dimension and epsilon is the precision, and you have an inverse of the precision, and you have an exponentiation of that. So actually you are saying is that it is NP hard. So if you have an NP hard problem, how do you solve it? The first approach is to approximate the solution. So where you trade precision for tractability. So you don't want precision, but you want tractability. You want to bring it to polynomial time or something. So you trade precision for tractability. The second, so if you look at gradient descent algorithms, like you are actually approximating the solution. You are not actually finding the solution. Except for linear approximation, you don't get solution in finite time. You always get it in the asymptotic sense. The second approach is to actually randomize the algorithm. So if you randomize the algorithm, you actually achieve tractability highly likely, or you achieve precision highly likely. So if you look at quicksort, for example, so what do you do? Quicksort, you randomize the pivot. So if you randomize the pivot, what you are getting is the running time on expectation is n log n, but in the worst case is n square. But always you get things around the expectation. So you are getting tractability highly likely. So if you look at the other case of say primality testing or something, where each time you give an input to the algorithm, the algorithm might say it's prime. It might say it's, even if it's prime, it says not prime. So there is a probability distribution over the correctness of the algorithm. So there is precision highly likely. The first case is tractability highly likely. So
So do you mean precision is highly likely?
Precision is highly likely, yeah. So you might get wrong answers, but on an expectation you always get correct answers. The expected behavior is good, but there is a small positive probability that you might get wrong answers. So let's randomize. So let's drop the approximation thing, see what happens when you randomize the optimization algorithm. So how do you do that? So let's take the case of a function being a Lipschitz function with constant k, and say the function's domain is 0, 1, and I uniformly randomly sample an input from this space.
Could you remind me what Lipschitz means here?
Oh, the growth is linear. The growth is linear. the growth of the function is linear. Okay, so function is Lipschitz if the growth is linear.
Changes.
Yeah, change is linear. Yeah. Okay, so yeah, so if you randomly sample from 0, 1 and see if you, so now the first question is, what is the probability that the sample that you get lies in the neighborhood of the global optimum? What is the probability? It's 2 epsilon by k, because you are in the epsilon neighborhood and you want your solution to be inside this. So it's uniform distribution, so it is 2 epsilon, and the Lipschitz constant is the one which controls the scaling of the point. So the input has to be in the x star neighborhood of epsilon by k. So the probability is 2 epsilon by k. Yeah.
So I guess there's many other points which could be epsilon close to the optimal value.
Yeah, optimal value. Yeah.
If there's multiple peaks,
Yes.
there's an optimal peak, and you might be epsilon close to that.
Yeah.
You might be epsilon close to another peak.
So
That's a lower bound.
yes, that's a lower bound. Yeah. Yeah. So okay. Okay. So how much is the expected number of trials you require to get one inside this event? So what is that? It will be the inverse of that, because you can see it as a geometric distribution. So the first n trials is a failure and the last trial is a success. So the expected number will be the inverse of that probability. So you can see it's like dependency is on the precision and the regularity constant. So it depends on the function and the precision. Again, so flat model doesn't work. So what you really need is, yeah.
The first blue line.
Yes.
Why does that probability depend on k?
You need the solution to be, so the probability distribution is over the input space and you are sampling from the input space. So you want to things within the x star neighborhood.
I mean, if it's just a function that's the optimum x star could be anywhere. Could be anywhere in 0, 1.
Yes, I am assuming x star is unique. Yeah.
And it's unique.
Yeah.
And we're picking a random point from 0, 1.
Yes, and assuming there are, yeah, fine, and
So why
this
would it
this
depend
event is
on
this set is
Lipschitz
connected and
constant?
everything. Yeah, sorry.
Why would it depend on the Lipschitz constant?
Oh, this neighborhood around x star, you need it to be within epsilon by k. Then only the function value lies within epsilon.
Oh,
Here,
that x is within.
yeah, x is within, because the probability distribution is over the input space.
Okay.
Yeah. So we have a dependency on the function and a dependency on the precision error. It's not good. So the flat model doesn't work. So how do you better it? You have to incorporate the landscape of the function into the distribution. So what do you mean by landscape? So you have, when you think about landscape, you think about the multimodality or you think about the structural irregularity. So when you are randomizing something, I think multimodality might be useful, but the modality of the function might be useful, but the structural restrictions, it might not be that useful. We'll see. Okay. So before we do anything about that, so we have to see what we are trying to achieve. So yep. So the thing is, we are trying to find the global optimum. So first thing you need is, how do you characterize the global optimum? So if you are looking at gradient descent, what you are doing is, the characterization of the limit point is the set of points where the gradient is 0, and you are trying to achieve that characterization. But here it's different. Our goal is to find the global optimum. So how do you characterize the global optimum? We don't have an analytic expression for global optimum, or at least can I approximate the whole thing? Say I can find a characterization for the set of events around the global optimum, set of points around the global optimum. So if you look at the gradient based thing where you characterize as the set of points where the gradient is 0, you have global optimum belonging to that set, but it's a much wider set. You want to narrow it down. So let's say this is the global optimum. I'll try to find the points which is close to that. At least that event I can characterize. So let's see one few of the characterizations. So I am asking, can I characterize global optimum? Is it possible to characterize global optimum? So let's look at existing characterizations. So the first one is from Laplace, which says that the maximum of the function is nothing but you take a positive function over the function, then you integrate it, and then you apply the reverse function, and then you average it. So what you are trying to do is you are taking the volume of the positive function of the objective function, and then you are reversing it, and then you are taking the average, and that average actually converges to the singularity in the sense of the global optimum. So this is by Laplace. The second thing is by Lebesgue, which says is that the global optimum is nothing but the fixed point of a particular function, and it's a unique fixed point. Unique fixed point, you have to think of it as take the level set, take the volume of the function over the level set, and you average it by the Lebesgue measure. It's just the length of the interval or whatever, if you're seeing it as an L1, so R1. So you take, again you are finding the density, and it says the density converges to singularity. So if you look at both these characterizations, you see is that you are actually taking the volume. Here you are taking the volume of the function over the level set. Here you are taking the volume of a positive function of the objective function, and you are actually averaging the volume, and you are achieving the singularity as limits goes to infinity. So what does it tell? It tells that volume is you need some kind of volume to actually characterize the landscape. So it says is that integration seems to be the key to explore the landscape of the objective function. So definitely not a flat integration, but you need some kind of weighted integration. Weighted integration in the sense integration with respect to some probability measure. So what we do is we inject randomization into the search through weighted integration. So how do we do that? So let's formalize the thing. So we are actually trying to bring in probability into the search system. So you're bringing randomization. So we need to formally define what is the probability system that we are trying to do. So let's start with the basic system. So we are saying we consider the set of all probability distributions f theta, which is parameterized, and f theta is the probability distribution over the solution space X. So to be precise, we consider the natural exponential family of distribution, because this is kind of too much abstract. So what you see is we just need to formalize, bring in a compact representation. So we consider the natural exponential family. So natural exponential family means the things of this form, where you have an exponentiation and there is a linear over the parameter theta. So if you look at all the existing things like binomial, Poisson, everything belongs to this one. So there's a very rich class of probability distribution. So let's deal with this one. So okay, so let's see how we can quantify things now. So you have an objective function, the black one, and say you have a parameterized distribution of theta. How do you quantify the high quality region? I am not going to quantify the optimum, I am going to quantify the high quality region. So high quality region in the sense something close to the global optimum. So how do you, like if it is a deterministic procedure, what do you do? Like you say h of x greater than or equal to gamma. So the gamma is close to the global optimum. That should be your characterization. But you have an f theta which actually is a probability distribution over the input space. So how do you do that? Now you say I have h of x greater than or equal to threshold. So it should be something is a level set, and since there is a probability distribution, you quantify the level set with the probability distribution. And then what you do is you want to make it unique, you take the soup of that. That does that make sense? And you, since it is a probability, you want the margins, so you keep a scalar. So what you are trying to say is you take the level set, actually is the complement of the level set. So we are maximizing. So let's call it level set again. So you are taking the level set and you are stretching the level set, and each time you are looking for the level sets whose probability is at least rho, and you are taking the soup of that. Soup you take means you get it as unique. Yeah.
The soup of all HL, HE.
No, all L or all the level thresholds.
Else, so
H is a scalar valued function.
and HU, HL is, where is that defined?
So this is the event, and the probability is at least rho. For all such level thresholds, you take the soup.
But where do you get the HL and HU? Is that given?
The function is assumed bounded. Assume it's given.
So I get the function,
Ah.
now I get to know that, but not where the soup is. I get to know that.
Yeah, yeah. I know the upper and lower bounds, not the true upper and lower bounds, but somewhere say like I know it become minus 100 and 100, but I don't know the exact optimum inside that closed interval.
So in your picture there, HL would be the bottom, the left side.
No, not this one or this one, but maybe things below or upper, like some naive information. But this is just an analytic form. You are not using it for algorithms. So this is fine. So you are taking all the level sets, you find the maximum level set, and then take the probability and find the soup of that. So but actually from the figure what you see is that this blue line is what this quantity is. So if you bring the line down, still the probability is going to be greater than rho, because you are having more points into that region. So the lines below this all satisfy this condition, but there will be only a unique thing which actually have the soup condition. So anything beyond that will have the probability less than rho, or anything below it the probability is still greater than rho. So you take the soup just to make it a unique thing. So actually you are quantifying this region, but that quantification has to come in the form of a scalar. The scalar has to be predetermined. So this is a neat way of quantifying this region. So yeah.
Sorry, actually, can we go back to that? please?
Okay.
So the value returned from the supremum, that's not a Boolean.
That's a scalar.
Right. Sorry. What is the value you're supposed to be returning from the supremum? Because
Yeah, L, super over L.
Yeah, that's what you're optimizing
Is it the
over.
arc soup? Is it the arc soup?
Yeah, that's what I'm thinking of.
No, actually you get something on the range.
On the range of H.
Yes.
Okay, so it's like the supremum of the set of all H
The values of
X
H beyond which the
such
function
that the probability of Hx greater than
is at least rho.
is greater than rho. Okay.
Yes.
That makes sense.
Okay. Okay, so that's the high quality event that we are going to look at. So now we have a quantification of this region. Now what we do next? We call it the high quality event. You have that threshold, and anything beyond that is the high quality event. So we have an f theta, we have an high quality event with respect to f theta. Now we are going to improve the theta. So how do we improve the theta? First so now we are going to truncate f theta into that region. How do we truncate it? Like just you can see it like you take the indicator function over that region, multiply it with f theta, and then take the integral. So you get a this is again a PDF, because the integral is 1 and it's always positive. How do you truncate it? Is actually the zero variance PDF, because the support of this f theta star is this region, because support means the set of points on which the function is not 0. So you can see that like this function has support only on this event, not anything outside the event. Is that okay with it? That's why it's called the zero variance distribution. Why? Because you sample using f theta star, you are always going to get points within that region, because the support of this PDF is that event. Is PDF because the integral is 1. It's always positive.
So you define the high quality event.
Yeah, this I define the high quality event, then I truncate the existing distribution to fit into that event.
But just because you define something doesn't mean you have it.
No, I'm just going analytically. So once we can bring the algorithm later into this. So this is the analytic form. Once you have a closed form analytic thing, you can actually approximate the thing. So algorithm comes after we have a formal expression.
Okay.
So this is the ideal case, then we use stochastic approximation to track the ideal case. Okay. So you have this thing. So this is good. This is the one which has 0 variance over this event. We have the high quality event. We have the distribution which has 0 variance over this event. The next thing is okay. So, but this is intractable. Why is intractable? Because this distribution may not belong to the class of functions we are considering. So how do we do that? So next, you have to approximate it. You bring in the Kullback labeler. So you have the target, you need a surrogate. So what you do is you find the distribution which is minimum in respect to Kullback labeler, but you go for the M projection. M projection because Kullback labeler is asymmetric. If you flip it, the metric is different. So you need the M projection means the moment projection because you need the support of f theta star and the f theta to be same, because we are actually dealing with supports. So you need the supports to be correlated. So you have to weight it with the target first. So the other case is the I projection where you flip it, but it doesn't work because the support is not going to be correlated. Okay, sorry. Okay, so just do the minimization. You get this, but this doesn't have the minimizing parameter, so you can drop this. You are left with this. It's a minimization. You have negative here. It becomes maximization, and this becomes the final optimization. Is okay with that? Okay. So the improvement rule says, given a theta, you find the elite thing, and then you can improve the parameter by just minimizing this optimization. It's just like any optimization problem where you, like if it's a gradient descent, you take one vector, one parameter, then you calibrate it by the gradient and get an improved vector. But if it's a policy improvement, you are getting one and then you are improving the policy. It's just like that. You have a distribution parameter theta, you solve this, you get an improved distribution parameter. So improved distribution parameter in the sense that the improved thing has much more weight in the high quality region compared to the previous one.
I'm going to ask a really stupid question. Where did theta come from? I thought we were looking for an x.
So we transform the problem from the x to theta now.
How?
We brought in the statistical models. We were operating on x, then we define distributions over x, and we are trying to randomize the thing by tuning the distributions. So I said if I just randomly choose it, you are not going to get a good one. So you are actually tuning the underlying sampling distribution, because the flat model has very poor performance. You have to tune the underlying distribution parameter, so that the next time you sample, you break that exponential dependency on the precision.
You're choosing a particular family.
To find the best one. Yes. So the flat model doesn't work, so you have to get a good one. So you choose a family, and each time you choose a parameter, and then you improve the parameter so that you finally converge to the best one.
So should I think of the family as being like a Gaussian distribution?
Yeah, so it's much more wider than that. So we consider the natural exponential. So it has the Gaussian in it.
theta is what?
Theta is some Euclidean parameter, Euclidean space. R to the power of d, the other operates in R to the power of n. So the issue here is d might be greater than n. So you are improving the dimension, but can it bring any additional properties is what we are going to see. Okay. See that. Okay, so you say given theta, you get an improved theta. So just run this algorithm multiple times. You take theta t, you improve, you get a theta t plus 1, you run it multiple times. It has to go to a convergence, just like you see in policy iteration. It should improve each time.
I'm going to ask some more stupid questions. To do step 2, it looks like it involves things we don't know.
Yes, so that's why we need to track them.
So it's not enough.
This is the ideal case, you need to track them. Tracking means you have to use some kind of estimation. So we can use stochastic approximation algorithms to estimate them, or you can use Monte Carlo sample averaging to estimate them. Yeah.
You have a distribution over a bunch of points, and so with each improvement step, are you reducing the variance?
Does it happen? That's what we have to see. Okay, so yeah.
So suboptimal f, if you find it, it doesn't mean that your end solution, I mean your end solution, the x that you will find later will deteriorate. It's just that it's optimal f will find that good solution later.
Yes, so each time it's improving in the sense of how the mass of the distribution is distributed over the high quality region. Each time you are improving means you are increasing the mass over that region, but gradually improving. But is it really improving is the question. So this is okay. So this is sorry. Yeah, this is the algorithm. So the next one is how good is the improvement. So if you directly apply the Pinsker inequality, you have theta, you have the high quality threshold, and this is the high quality region. So the probability of the next one, how good it is, it says that it is 1 minus the approximation error. So it depends on what is the space you are projecting to. So if the NEF can have good approximation properties, then this is going to be very low and you are getting a good high probability. But we don't know the bound on this one. So because I don't know, so let's keep it that way. The next thing is how good is with respect to the previous parameter. So this is the high quality region with respect to the previous parameter, and this is the probability, and what we can do is by simple arithmetic you can find that the probability of the new one over that region will be greater than the previous one. So there is an improvement, because what I said earlier is like theta t is the previous one, you find the elite region, the probability with respect to the new one will be greater than the probability with respect to the previous one. So mass is improving over that region. Does this make sense? Confused? Is it okay, this one still? Okay. So what about the expected behavior? So what it says is the expected behavior of the new parameter is just the sufficient statistic of the natural exponential family is equal to the optimal parameter, and the optimal parameter is better than the previous parameter. So the expected behavior is improving. So the probability is improving and the expected behavior is also improving. So it's good. So it's always good. So okay. So finally, when you study the theta t performance, it says is that it converges to the standard theorem. It says internally chain transitive set of a particular ODE. So whatever you bring into the system, it finally boils down to a deterministic system, and that deterministic system is nothing but the gradient of some nonlinear function. So the whole procedure that we did on that problem boils down to a gradient flow. Whatever the randomization we instilled into it, it just averaged it out. But does this averaging helps in some way or not? That's what we have to say. So it's just the assumptions are like the Lipschitz continuity and everything. So finally it says is the every randomization you put into the system boils down to a deterministic system. Deterministic system. Okay, so you have to see a bit more of that. You are seeing the behavior of the mean, not the theta. So you have theta, you are updating theta in the recursions, and you are looking at the mean behavior. Why do you want to look at the mean behavior is that the mean behavior space becomes flat and the other thing is curved or something. So you have to look at the mean behavior. So if you look at the mean behavior becomes equivalent to a ODE which is deterministic. And what do you gain from this? So really says is that you have the optimization problem or X, you bring in all the randomization, finally boils down to a different optimization problem, and you are doing a gradient descent. Gradient ascent. But what is the purpose of all this? So when I transform it, is the multimodality turning to unimodality? That's the first question. So are you doing convexification? The second question is the structural irregularities, is it getting smoothened out? Are you getting a smoothening? Definitely smoothening is coming, but we don't know about whether it's becoming a convex function. Why we don't know is that we have counter examples. So something like this, where you can show that it doesn't go to the maximum here, even though there is only one maximum. Here we have again one maximum, but it doesn't even converge to a point, it converges to a set. So this is complicated. So what you're really seeing is that the claim what we thought was the transformation might help in convexification is not happening, but it definitely have irregularity to regularity is happening. So yeah, again let's leave that part. So what we thought is, so these are counter examples, but you get global optimums in many other cases. So how do you characterize such a behavior? You have counter examples where it shows that it doesn't converge to the global optimum, but we have a lot of examples where it converges to the global optimum. So how do you characterize such a behavior? So what we did was we slightly modified the recursion. So this was the previous recursion, we just added a weight function into it, and we started mixing it with some initial distribution. So the whole update procedure changed to bringing a weight function and then mixing it with the distribution, and the NEF was not strong enough, so we consider the Gaussian space. So everything is trimmed down. Now we see what will happen if the distribution space is Gaussian with some slight changes to the optimization. So with Gaussian you have nice gradient procedures. These are just stochastic approximation versions, but what you really get is this one. What it really says is that if the distribution is Gaussian and you have an initial distribution which is independent, mutually independent, and the marginal variances are all same, say like Q, and some regularity constraints, when if the function is twice continuously differentiable, then the model sequence actually converges to the degenerate distribution concentrated at the global optimum. That means that, as you said, the variance is decaying and the means are all converging to the optimum. Just for the case of Gaussian, you cannot claim such claims for NEF. But this is a conditional requirement. You says that it only exists for all q which is greater than q star and for all r greater than r star. So the weight function that we added is just like the exponentiation function. So it's just like what you see in the Laplace thing. So here what the Laplace expression is, you exponentiate the function. What you are really doing is when you exponentiate the function, you are actually widening the gap between points, the function values. You are stretching the function values, and k is the scalar which controls the stretching. So when you add this weight function to it, actually you are in the integral you are actually differentiating the function values, and when you parameterize as e to the power of r x, when you say that if the function is e to the power of r x, you are actually parameterizing in terms of r, and that means you are controlling the stretching, and you are saying is that for a given function it depends on the initial distribution and it depends on how much you can stretch. So there is a stretching threshold, there is an initial distribution constant, anything beyond that, if you use such values, the convergence to a degenerate distribution is guaranteed, and it's almost surely. Only for functions which are twice continuously differential. So this is the result. Let's see some experiments. All these are all benchmark functions, Levy, trigonometric, whatever it is. Each time you run it, the red one is ours, the others are like other global optimization algorithms. So the red ones always converge. And yeah, neatly, yeah. So other cases, some more converges. That's true. So this plots the dependency, how it goes. Like we said, it depends on the initial distribution, it depends on the scaling factor r. So if this is the true case where the convergence happens to the optimum, the Gaussians are all converging. If you change the q to a lower value, here it was different, it was lowered because the initial variance is reduced here, it was much wider here. Then the convergence is to a local optimum, and when you play around with r was 2, you said something greater than r star. So if you reduce the r, things get flattened out because it's not able to stretch that region, you just isolate the points actually, so it gets exploded. So there is the dependency which is being verified by these things. Yeah, so the next thing is, how does it depend on the row, the scalar? So it should converge for every row, that was theorem says, but actually for a particular range of values, like some say 2, 3, 4, 5, 2, 3, 4, 5. So in this interval it converges very fast. For other ones it is very slow, because the row is the divider which decides the threshold. So if you take row very low, if you take the row very low, so if you take row very low, this is going to go down. So you have, so if you take row very, so this is going to go down. If you take row very high, things are going to go down. So the support is not contracting sufficiently fast. If you take row high, the support is contracting pretty fast, and so but the variance remains high, so you can't actually converge. So can I use it in the RL setting? So just some experience. So I did it in the prediction setting. So what you do is you just take the MSPB, because I need an objective function to minimize. You take the MSPB, you isolate the stochastic and the deterministic part, then you write the stochastic part like this, and then you track the stochastic part. Use a simple stochastic recursion to track the stochastic part, and then you just run the same algorithm on top of that, and then you can prove that this tracking actually tracks the MSPB, and once it tracks the MSPB, you run the same the optimization scheme, it converges. So if you look at the Bayes 7 star, you can have some convergence. So Bayes 7 star has this property that TD will converge only for gamma less than 0.88, and TD will diverge for gamma greater than 0.88. So 0.88 is the threshold where the Bayes star where TD diverges. So 0.9, if you take, TD doesn't converge. For less than 0.88, TD always converge. So if you test it, like things you, yeah, the red one is converging pretty fast. So that is a quadratic version. So how do you make it a linear version? You take the first order Taylor series expansion of the MSPB. So MSPB can be written as the true MSPB plus the linear version. So but there is this reference point that comes at each point. So how do you take the reference point? So you have a underlying distribution theta, you take the mean as the reference point, because whenever you are sampling, the things has to remain close to the mean, likely, not highly likely. So you take that as the reference point, and you take the first Taylor series expansion, you get a linear algorithm. Then you can compare that. The red one converges faster. Here also converges faster. TD diverges, GTD, TDC may be a bit slow. You can use it in control. Yep, fast policy search. SPSI is actually a gradient descent version, and MRAS is also some kind of global optimization algorithm. Yeah, the thing is, we get so in the case of this one, the optimal reward is 0 because you have to make it all horizontal, and the algorithm actually finds the optimal policy. In this case also 0 is the optimal, and if most of the algorithm converges except for the gradient based system. So yep.
We're running rather over time, but
Yes, sorry.
Any quick questions? Good.
Yeah.
For the control experience, previous slide, what was the objective function that you used?
I took the weighted norm of the value function with the steady state distribution of the behavior policy. I use a of policy thing, so I used a behavior policy, and I assuming it's ergodic, so the weighted norm with respect to the steady state distribution of the, because it's a value function based approach that I used. So at each iteration, each policy, I need the scalar version of the value function. So I scalarize the value function by taking it as the weighted norm.
Okay, thank you very much.
Thank you.